Welcome to another section of the machine learning development life cycle. We shall be discussing training and optimization. With training, we are able to get the best parameters for our model. And with optimization, we are able to do this training as quickly as possible, or better still, as efficiently as possible. So we have the linear regression problem. Say we have this and the gradient descent formula theta I equals theta I minus alpha partial derivative of the loss with respect to theta I. Note that theta I is a parameter which is to be optimized such that the loss is minimized. Now let's look at this curve. We have the loss and we have theta 1. That's in the case of linear regression, where we just have one weight, theta 1. We're trying to optimize. Although today, in many problems we face, we have many times millions of weights. So we have this curve, and our aim is actually to select theta 1. Note that this is not 0. This point here isn't the origin. So if this were the origin, we're simply saying that every time theta 1 is 0, we have our optimized value. But this is not actually true. So the origin may be found at a different point, and we're just trying to look for the value of theta 1 for which this loss is minimized. Now, say we at this point here. At this point, we have a specific value of theta 1. So let's understand how this gradient descent algorithm works. At this point, we have a specific value of theta 1, which you could get somewhere here. Now, drawing a tangent at this point and calculating the gradient at this tangent is similar to finding the partial derivative of L with respect to theta 1 at this particular point. That's from our calculus course. So if we are at this point, we're going to have the L, or this partial derivative of L with respect to theta 1 being positive. So we're going to, since this is a positive slope, so we're going to have a positive value here. Now, if we put in the positive value, we find that we have theta 1 equals theta 1 minus, suppose alpha is a positive number. For now, we're not going to talk much about alpha. So we have this alpha, which is a positive number, times a positive number. Obviously, we're going to have theta 1 minus a positive number. So we find that this theta 1 will tend to move to the left. So we see clearly that if we had to say theta 1 equals 2, and this alpha times this gives us 1, for example, we're going to have 2 equals 2 minus 1. So 2 will become 1, or theta 1 will become 1 from 2. So if theta 1 initially is 2, here we have 2 minus this gives us a 1. So actually, this term permits us to go a step ahead, or a step towards the direction of the minimal value, or towards the direction which will minimize our loss L. Now, say we've done this and we've moved this step. So we've moved from this point to this other point. So we have done this actually because we've left from theta 1, which was here, now to this point, and that's because of this step, or this gradient descent step. Now we've done this and we'll still have a positive slope. This positive slope further tells us to move in this other direction, in this left direction. So we find that this gradient descent algorithm or equation helps us to move in the right direction. So it's some sort of guide which tells us in which direction to move. And then we move and we go this way, and we have this. So we'll find out moving this, or selecting a very good value for alpha, which now turns out to be the learning rate. So don't forget that while training, we actually trying to teach this algorithm how to behave, or how to select the best values of theta I such that the loss is minimized, hence the name learning rate. So we're trying to learn some parameters, and then the rate at which we learn these parameters is going to be affected by the value of alpha, which happens to be our learning rate. Generally, alpha takes values like 1, very rare cases, 0.1, 0.001, 0.01, 0.0001, 1 e to the minus 6 and values like that. So generally alpha takes very small values such that we kind of go gradually towards this minimal value. Now we use the term generally for the choice of making alpha because finding alpha or choosing the best alpha for our training isn't something that's actually fixed. So we kind of learn how to better choose alpha by working with many algorithms or by solving many problems. So the more you're going to work with problems or solve problems, you're going to better have an intuition on which value of alpha to start working with, as the value of alpha can be modified even while training. Now suppose we were at this point. Now if we are at this point, the tangent gives us a negative slope, so we have this negative slope. So if we're at this point with a negative slope, we have alpha, which is a positive number, this is a negative number, so positive times negative gives negative, and then we have theta I minus a negative number, which gives us theta I plus that number. So if we had theta 1 initially to be 2, let's replace here, we have this 2, and find the partial derivative at this point gives us negative 1. For example, we're going to be having 2 minus alpha times negative 1, and if alpha is say 1 or any positive number, let's say for example 0.1, we're going to have 2 minus 0.1 times negative 1. Now this negative comes out here, we have 2 plus 0.1 times negative 1, it gives us 2.1. so leaving from theta 1, which is 2 initially, we're going to leave from here and go a step to the right, and this takes us towards our ultimate value of L, which is this L which is minimized, or this L which has a value below which we can't go any further. Now let's go back to the previous case where we had positive gradient. So in this case, we had seen that we had 2 minus alpha into 1, and if alpha equals 0.1, we have 2 minus 0.1 times 1. So we have theta 1 leaving from 2 now to 0.9. So we see how we go a step to the left and a step towards our point, our optimal point. Now let's see how this algorithm works visually. So suppose we have this point initially, we're gonna move this step to the left and then to the left, and then as we go and right up to our optimal point where we're gonna stop. But now notice that with this kind of loss function, which we had seen earlier to represent the mean square error, the more we get closer to the optimal point, or this minimum value or this minimum point, the more these steps get smaller. Now the reason why these steps get smaller is simply because as we go, this gradient of the slopes gets smaller. So we saw that here we had this very steep slope, and then we moved on to this, and then to this, and then the more we go, the more the slope turns towards 0. And simply because of this, we have this value which is becoming very small. So if this value is becoming very small, the rate at which, or the way in which we going to modify theta I is going to be reduced. So if initially we had this kind of slope, there's going to be a great change in theta. But now when we get to a point like this, for example, where the slope is kind of reduced, or the gradient of the slope is kind of reduced, then these changes in theta I are also minimized. Hence the advantage of the mean square error over the mean absolute error function. Now let's look at this other case. So we have this, we could take a step back. So we have noticed that if your value for alpha is very large, so it's true we said initially that alpha could take values like 1, 0.1, 0.01, 0.001, and so on and so forth. Now, it should be noted that for even some problems, choosing a value like 0.001 is going to lead to divergence. Now, what's divergence about? Divergence basically occurs whenever we choose a very large value for alpha. And this value for alpha depends actually on the problem. So in some cases where for alpha to be say 1, we'll still have convergence, while in other cases when alpha is 0.001, we're going to have a model that diverges. So let's see exactly how a model diverges. So if we are at this point initially and that our alpha is kind of very large, we have something like this. So instead of the kind of small steps we generally have, like we saw when the model was converging towards this minimum point, or in this case our alpha, or the fact that our alpha is kind of large makes it that these changes are kind of increased in a way. So instead of having the small steps, like say in this case we had alpha equals 3, we'll have 2 minus 3 times 1, so we go from 2 to -1. So in this case we'll be going from here. Initially when alpha was 0.1, we left from 2 to 0.9, but now if alpha is 3, we're going to leave from 2 to -1. So we see that there's a great change in the value of theta 1. Now let's look at this visually. We have this, so we see that it could get to a level where once we reach near this minimum point, we instead even skip it. That's because these changes are very large because of the learning rate. We tend to like come and skip this value and move to this other point, and then this effect kind of continues all the way. So instead of going from this point maybe back to this minimum point, because of the very large values of alpha, we could even go again further away from those minimum points, and then we could have something like this and this. So we kind of go out of this bowl, we could say. Now this is very dangerous, and it could be solved by choosing an appropriate value for alpha. It should be noted that for some problems, choosing alpha equals 1 may lead to convergence, and for others, choosing alpha equals 0.0001 will still lead to divergence. So the hyperparameter alpha has to be well selected, or the learning rate has to be well chosen. Now let's look at the mean absolute error we had seen earlier under the error sanctioning section. Now we had seen that the mean absolute error had a disadvantage compared to the mean square error, and that disadvantage was simply the fact that the more we go closer to this minimum point, these changes actually aren't reduced. So unlike here where when we're converging, these changes are reduced because the gradients of the slopes are actually reduced as we go towards this minimum points. But in this case, these gradients don't actually change. So we have a fixed gradient from this point right to this minimum point. So it kind of makes it very difficult for the model to converge easily. So we have this visually and this. So this is an ideal case, but this may not always be the case, as we could instead face divergence even after choosing the value of alpha appropriately. Now let's leave from this kind of schematics to something like this. Now this actually represents more of what we see in real world problems. Although generally, as we said, the theta, we don't only have one parameter like theta 1 here. We're using this because it's actually easier to visualize it in the 2D surface. Now let's visualize how convergence, or how this model with this loss function is going to learn the parameters theta 1. So suppose we're starting up this way. We have, if we're at this point, for example, we could leave here and get to a point closer to this global minimum. Now note that there are local minimas and there is a global minimum. So we could see this point right here and this other point as local minima, simply because around them there happen to be the smallest or the minimum points as compared to the others, or compared to the other points surrounding them. Now looking at this other point here, comparing it to this other points in this, say, zone or in this locality, we have that this could be called a local minima. Now, for taking into consideration all the points or all the different possibilities, we have just one global minimum, which happens to be this. So we have this as a global minimum and we have some local minima. Now let's continue with this convergence. So we have this, it moves to this step, and then this, and then it goes downhill, gets into this valley, which is a local minima, it goes up, then comes back. So when training a machine learning algorithm, our aim is actually for us not to get stuck in any of this local minima or any of the saddle points. So with this, we could say we have this local minima, we have this local maxima, and then we could have this saddle point. The way we could define a local minima, or this any point which can be termed a minimum point, is quite simple. If you have a point and that to move in any direction away from that point you can only move upward, then that point is a minimum point. If you have a point like this one where the way to move in any of this direction is if you move this way or move this other way, you're going to be going downward, then that point is a maximum point. But taking this other point right here, if we take this other point here, we have that if we move either way, like if you move to the left, you have you're going up, and if you move to the right, you're going downwards. So this is now what we call a saddle point. Now suppose we're working with two parameters, theta 1 and theta 2. So we have this plot with on this axis theta 1, this theta 2, and then this upward L. Now let's look at this loss function with respect to theta 1 and theta 2. We could see straight away that we have this point, this point, this point, denoting local minimas. We have this global maxima or local maxima, sorry, and then at this level, that's this particular point here, we have a saddle point. That's simply because going in this direction, you're kind of going upward, and in this other direction, you're going downward. So suppose we started initially our training when theta 1, theta 2 fell at this point. We find that our algorithm can move this direction, it could move this way, move downward, go downward, 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 and finally end up at this point. So which will make it quite difficult for us to leave from this point and go to the global minimum point, which is kind of like the aim we're trying to achieve here. But then getting to this point where you may feel like it's converged already, as you get into this kind of point while doing the training or during a training process, the loss may not change very much, and you may feel like, say, you could stop the training and then use the parameters in doing whatever testing or predictions you want to do. But then it's also advisable sometimes to just keep the model training, as you may come sometime and see that it is actually left from this point to a more reasonable point, or say in the best case scenario, even the global minimum point. Fortunately, as we increase the number of parameters, that is, as we move from 2 parameters or from 1 parameter to 2 parameters, and then to 3 parameters, to 4, to 5, and then to a million and even billions of parameters, the local minima problem actually is reduced, as we have fewer local minima to deal with. Instead, the most common problem we face generally when working at higher dimensions is the problem of having saddle points. And this may lead to a slowing of the training process. Another common problem is the vanishing and exploding gradients problem. For vanishing gradients, actually, the gradients, as the term go, vanish with time, or as we go deep into the architecture or into the model. So we could have a situation where this partial derivative with respect to a particular parameter is very, very small, such that these changes are very minimal. So we don't really have the value of theta changing that much. So that's a case of vanishing gradients. Now with exploding gradients, we have a case where these values of or these partial derivatives are actually very, very large, and in that case it's very difficult to converge or to find the suitable values of theta very easily. Nonetheless, this particular problem is kind of faced very much with recurrent neural networks, which we shall work with subsequently, and the LSTM networks actually come to solve this problem of vanishing gradients. But in the case where we have exploding gradients, we could use a method or technique known as gradient clipping, wherein the value of these gradients cannot cross a particular threshold. So once it crosses that threshold, we actually clip it and make sure it doesn't cross that threshold. Now that we've seen the gradient descent algorithm and how it works exactly, we're going to move to how to calculate this partial derivative of the loss function with respect to each and every parameter whenever we're given the loss function. So for the linear regression algorithm, say we have these two elements in our data set. This is very uncommon, as generally we aim to have thousands and even millions of elements in our data set, or millions of data points. In this case, we're choosing our M, that is the number of data points, to be just 2 for demonstration purposes. So here we have the class R's, the quiz, the final mark, and the status. So this is for the linear regression, and this for the logistic regression. Now, we defined earlier that our loss was equals 1 on M, the sum of the output minus the target output, all of this squared. Let's find the partial derivative of the loss with respect to each of the parameters theta j. This derivative can be given as the partial derivative of theta of the loss, which is actually this. Now note that the loss is this, so we have all of this representing the loss with respect to theta j. Now from calculus, we have that the partial derivative of a plus b with respect to say x is equals the partial derivative of a with respect to x plus the partial derivative of b with respect to x. That is, we're supposing that a is a function of x and b a function of x. Now, this can be generalized as the partial derivative of a sum is equals the sum of their partial derivatives. Now, in this case, we have the partial derivative of this sum is equals the sum of the partial derivative of each of these elements. In this case, where we had m equals 2, we're going to be having sum from I equals 1 to 2. So we're basically going to be having this when I equals 1 and plus this when I equals 2. Now, the derivative of all of this sum is equals the sum of the derivatives of each of these terms. So now we're going to be having when I equals 1, the derivative of this when I equals 1 plus the derivative of this when I equals 2. So which comes back to this. Now, we also have that the derivative of a plus or minus b of x. So here we're considering that a is not a function of x. So we have a plus or minus b of x, all of this squared, is equals b prime. So we're using or applying the function in a function rule, wherein we're taking what's in the function, that's all this, that's a plus or minus bx, we derive it and it gives us b prime of x. That's because a is a constant since it's not a function of x. So here we have the derivative of b of that is derivative of b of x, which is b prime of x, into the derivative of all this, considering that a plus or minus bx is, say, a big X. So in that case, we have a plus or minus bx now times 2, because we take this 2 and we send it down, and then we have 2 minus 1. So that's why we have b prime of x into 2 into a plus or minus b of x. So you could check on our calculus course to make sure you understand these concepts right. Now, having done this, we could actually find the derivative of this function here. In this case, we have the derivative or the partial derivative of this with respect to theta I. So let's look at this keenly. We made an error right here. It's actually with respect to theta j, since we're working with j. So we have this partial derivative with respect to theta j. Now let's look at all the different values we have in here, and look at the points where we have theta j intervening. So we notice that it's only here we have theta j, because here we have theta 0 x0 plus dot 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 right up to theta j xj plus right up to theta n xn. Now in this particular case, we have theta 0, theta 1, and theta 2. So if we're looking for the partial derivative of L with respect to theta 0, then our theta j in this case will be theta 0. So that's actually how we could look at it very easily. Now in this case, we have this, and now we're trying to derive this with respect to theta j. So theta 0 x0 up to theta n xn, while keeping out theta j xj minus yi target is actually representing a that we had here, and b of x is represented now by theta j xj. So we have this theta j xj, which is the only part of this whole function which depends on theta j. Now, as we saw earlier, deriving this will entail just deriving this part. So if we derive this, now we have theta j xj, the derivative of this with respect to theta j will give us xj. So we're saying this xj now like a constant. So deriving a constant times the variable theta j will give us xj, and that's why we have xj out. But now take note that we're doing all this for I equals 1 to m, and for this particular term it depends on I. So that's why here, instead of having just xj, we have xj with respect to a particular I, as we move from I equals 1 to m. So we have xj of I, and now we have all this with 2. So this 2 comes from this. We have seen this already, and then we actually replace our function as a plus or minus bx. So yeah, that's basically what we have here now. So for us to see this a bit clearer, we could rewrite this as what we have here. So here we have theta 0 x0 right up to theta n xn, but it should be noted that we are omitting theta j xj. So in this case, we have all this without this term, and then minus yi target. So we have this. So actually what we've done here is we've regrouped all these terms which do not depend on theta j, which do not depend on this theta j we have here, and then we've regrouped all the terms which depend on theta j on one side. So it looks like this a plus or minus bx we had already. So we have this as a now plus b of x, or plus this function. So that's exactly how we look at this, and that's how we find ourselves living from here to this. And now once we have this, we could rewrite it as 2 on m, the sum of xji. Now note that this is actually yi pred. So it's kind of the function you have, or the output you have when you use the model or the linear regression model. So this is what your linear regression model outputs, and this is what is expected to output. So that's the yi target and the yi predicted. So this is how we have the partial derivative of the loss with respect to each of the parameters theta j for our linear regression problem. Now let's rewrite this our data set. So we have this 1 1. Now recall that we had seen the notion of bias previously. So here we have kind of like created a column for the bias. So we have 1 73 12 13.2. Then we have 1 15 16 9.5. Now for now we're not dealing with the status since we're dealing with a linear regression problem. Then we have x, so we kind of extract x from this. So we have x to be this section, and then we have y to be 13.2 9.5. Once this is done, we could also see how our theta can be written as. So we have theta, which is theta 0, theta 1, theta 2. Since in this case we have 3 different columns for x. So we have this column, this, and they each have values for theta. In this case, theta 0, theta 1, theta 2. And also, for each of these theta, we have to calculate the partial derivative of the loss with respect to the theta. Now, recall that we're doing all this because we need it in our gradient descent algorithm, wherein to find the new values for theta, we need also the partial derivative of the loss with respect to theta. Now, generally, let's consider our alpha to be 0.01. So we shall go step by step, or we shall redo this step by step so that we see how with a Python programming language it's quite easy to implement this algorithm. So suppose we have theta 0 new, which is equals the initial theta 0, which is here written as theta 0, minus alpha, the partial derivative of L with respect to theta 0. This can be written as theta 0 minus alpha into, like, we replace what we had here in, or taken from this formula, we'll simply have this. So here we have 2 on m, which is getting from this. Here we have m equals 2. So that's also the reason why we chose this, because we wanted to use this example, and making m to be large is going to make us redo some steps a lot. So here we just have m equals 2. So that's why we chose m to be 2. So, and we have for the first case, so note that from this point to this, it's kind of like I equals 1, and then from year to year is I equals 2. So for this first case, we have xji. Now, what's xji? Now, before looking at xji, it's important to understand what is j and what is I in this case. First of all, for what we're looking for here, we have our j to be equals 0, since we're looking for theta 0. So our j in this case is 0. Now, what's our I? For the first case, I is 1, and for the next case, I is 2. So for this case, we're looking for x01. Now, what's x01? To find x01, what we simply do is we have, from looking at our x, we have 0, that's this first column, and then 1 is the first row. So we have 1, and that's why here we have 1. So we repeat again, we have x01, the first column, and 1 is like the first row. Now this doesn't conform with kind of the matrix notation, but it's very easy to understand. So with this, we have 1 into, we have the output of our model. Now to get the output of our model is kind of straightforward. We simply take each of this, that's for this first row, we take all this and multiply by the theta zeros and add them up. So we have 1 times theta 0 plus 73 times theta 1 plus 12 times theta 2, which is this, and all this minus 13.2. So recall we have our theta j xj, or our theta j xj, the sum of this theta j xj minus the output y. So that's it here. And then now we moved from I equals 1 to I equals 2. We still have our 1 here because we're dealing with 0 as j. So far as j is 0, we'll always have here 1. So we'll still have 1. We have theta 0 times 1, which is this times this times this, plus 15 times theta 1 plus 16 times theta 2 minus 9.5. So that's what we have here. Now we'll move on to the next. Suppose we're looking for theta 1 new. So this is exactly how we'll find a new value for theta 1 or for theta 0. Now let's go on to theta 1 new. For theta 1 new, we have theta 1 minus alpha into 2m into these two terms. So when I equals 1 and when I equals 2. Now when I equals 1 and in this case j is equals 1, so we are looking for x1, that's x1 1. Now let's look at this. We are on our first row, and then we're looking for when j equals 1. Now notice that, or recall that we had j moving from 0 to 2. So we have, this is 0, this is 1. So we are on the first row, and then this column, so we are at 73. That's why here we have 73. And into, now we're working with this first row. So we have 1 times theta 0 plus 73 times theta 1 plus 12 times theta 2 minus the output 13.2. And then plus, for the next we have 15. So we simply take from here, since we're still working with j, this column, and then we're working with the second data point. So we're having this 15 into this minus the output 9.5. So that's what we have here. Now this is repeated for theta 2, and then we could rewrite this matrix or the matrix theta as theta, or this new matrix of theta as theta 0 new, theta 1 new, theta 2 new. So they actually occupy a column, and this is equals theta 0, theta 1, theta 2 minus all this. So we shall see exactly why we using all this. That is, we're going to solve this and see how it comes back to these three equations we've just done. So we have theta 0, theta 1, theta 2 minus 2 alpha on m into x transpose into x theta minus y. Now this x transpose basically is the transpose of this. X times theta is this times theta, and then y is this we have seen already. So this is equals theta 0, theta 1, theta 2 minus 2 alpha on m into, this is our x transpose into x times theta minus y. Now simplifying this, we have this minus 2 alpha on m into x transpose into this times theta 0, theta 1, theta 2. Now multiplying here, we have 1 times theta 0 plus 73 times theta 2 plus 12 times theta 2, which gives us this. And then here we have 1 times theta 0 plus 15 times theta 1 plus 16 times theta 2, which gives us this. And all this minus 13.2, 9.5. So here we have this 2 by 1 matrix minus another 2 by 1 matrix. This results in a 2 by 1 matrix, which can be given as all this minus 13.2 for the first row and all this minus 9.5 for the second row. Now we take this and multiply by this 2 by 1 matrix. So in this case, we have this 3 by 2 matrix times 2 by 1 matrix, which will lead to a 3 by 1 matrix. And multiplying this, we have this new matrix. So we could take the first step. We have 1 times all this. So that's why we have 1 times this minus 13.2, which is this first row, plus this 1 times all this minus 9.5, which is the second row. Now, if you have any doubts with all these calculations, you are advised to look at our linear algebra course. So we have, that's how we get this first row, and then we repeat this to have the second and then the third row. Now, what do we notice? We notice that using this formula or using simply this technique, we find that the new values for theta happen to be the same new values for theta we had previously. So we had this, if we look back at this, we have 1 into theta 0 1 plus theta 1 73 plus this minus 13.2, which is simply this, plus 1 into all this, which is this. And then for the next, if you look at this, it's going to be this. Next, if you look at this, you still have this. So with this in mind, it simply tells us that if we're to do some calculation, or if we are writing a program to help us calculate the partial derivatives of L and then find the new values of theta, it will suffice to simply use this or use all this equation. So we can say that when working with a linear regression model, our partial derivative of L with respect to theta can be given as x transpose into x theta minus y. divided by m times 2 alpha, or times 2, because alpha is separate from the partial derivative. And then we have theta, or the new theta, or we update our theta such that we have theta minus all of this. So this is going to help us greatly in our Python programs, or any other program, or in any program you could do in any language. Now, this technique, because normally or intuitively you may feel like you should have used maybe a for loop to go through each of the thetas. That is, you may say, okay, for I going from 0 to 1, like in this case, for I going from 0 to 1, you shall find the partial derivative for each of these terms. So you may be tempted to use a for loop in getting all of this. So we could go for I equals 0, you use this formula, or you simply use this formula, and then you get the partial derivative, and then you apply the gradient descent algorithm. But then this isn't very efficient, as with this we make use of a technique known as vectorization. And while using vectorization, and especially on graphical processing units, that's GPUs, it kind of speeds up the operations. So in practice, we try as much as possible to vectorize any solution we're trying to work with. Now, we could also have our loss given to us as 1 over m, the sum of x theta minus y squared. Now, this dot squared simply means it's an element y squaring. So we're not going to take x theta minus y times x theta minus y. No, we're going to have x theta minus y, and for each and every value of x theta minus y, we're going to square it. So doing that, and then later on, for the new matrix we obtain, we sum it all and then divide by m, is going to give us the L.